So, good morning all. Today we will see the last section of our first module. We will start with the equation of continuity, otherwise known as law of conservation of electric charges for time varying system. Del of J equals minus dou rho V by dou T. This term shows dou rho V by dou T gives you the rate of change of charge per unit volume, and that rate is decreasing. That is why you are having a negative sign here. And del of J, it is a divergence. Del gives you the divergence, and divergence gives the total outward flow of flux in a charge. It is written del J is a net outflow of charge per unit volume in unit time. So this is the mathematical representation of equation of continuity. Del of J equals minus dou rho V by dou T, and negative sign shows you that the rate is decreasing. That is stated in this sentence. The law of conservation of charge demands that the total charge that flows out through the surface in unit time is equal to the time rate of decrease of charge contained in the volume. Now, the above equation is for a time varying field. Suppose the field is steady, then the rate of change of charge per unit volume rho V will be a constant. For a steady field, then dou rho V by dou T will be equal to 0. So we can rewrite the above equation as del J equal to 0 for steady state. So these two are the equation of continuity. This is del J equals minus dou rho V by dou T for a time varying field, and del J equal to 0 for a steady state. Next we will see the term current density J, which is defined as current per unit volume, and J is equal to sigma E, where sigma is the electrical conductivity of the medium. We have one more expression for J, that is equal to rho V. If we are using this expression, then that J is the convection current density. Okay, convection current density. So these are the two different formulas for current density. J is equal to sigma E. This is the conduction current density, and J equal to rho V is a convection current density. Actually, this is more important. Okay, J equal to sigma E. So this equation you can by heart. Now, this is a closed surface, and this is your current density J, and here you are taking a small area ds. Then I can write di, elemental current I, is equal to J ds. Okay, elemental current di is equal to J ds, where J is a current density and ds is the elemental area or small surface area. From that you can write I is equal to surface integral of J ds. One thing that you have to keep in mind is, if across the integral there is a circular sign, then that means the surface is closed. Okay, so that circular sign is used to indicate that you are trying to find out a particular parameter across a closed surface. Okay, so this is the expression for current I is equal to surface integral J ds, or you can write it as surface integral J dA. Since you are using dA here you have to use A. Okay, you can use any, both are the same, there is no difference, only the difference is in the representation. Here you are using ds for surface area, and here you are using dA for surface area. So for examination it's enough to write any one expression. Okay, next we will see what is magnetic scalar potential. It is a term which is analogous to the electric potential E equal to minus del B. Okay, you have what is the relation connecting electric field intensity and potential E is equal to minus del B, where E is electric field intensity and V is your potential. So similar to scalar electric potential, we have scalar magnetic potential for the description of steady magnetic field. However, the scope of such a potential is limited due to various reasons. Scalar magnitude potential works well for a permanent magnet and current-free region. Analogous to electric potential, E equal to minus del V. Here E is electric field intensity and V is the electric potential. Okay. We define the scalar magnetic potential as H equal to minus of del Vm, where H is the magnetic field density. Okay. And Vm is a scalar magnetic potential. Now I am going to take curl on both the sides. So I can write del cross H is equal to minus of del cross del Vm, where del Vm, you know, it is a gradient of a scalar function. If there is a notation del, then that means it is a gradient of a scalar function. And you know, potential is also a scalar quantity. So we know curl of gradient of a scalar function is equal to 0. Okay. This point is important. Curl of gradient of a scalar function is equal to 0. So here this term is a gradient of a scalar function. And if you are taking the curl of this term, it will be equal to 0 according to this definition. Okay. So we will get del cross H is equal to 0, where H is a magnetic field intensity. Now, in the Ampere circuit law, we have studied del cross H is equal to J. This is another form of Ampere circuit law. You can go through this under the section Ampere circuit law of magnetic field. Okay, there you can see this expression. Del cross H is equal to J. Now you can see these two expressions are really absolutely contradicting, right? Because here you are getting del cross H is equal to 0 and here you are getting del cross H is equal to J, and we have derived both these expressions for magnetic field. So how is it possible? For same field you are getting two different equations, del cross H equal to 0, del cross H is equal to J. So because of this, we have to redefine magnetic scalar potential. That is, the scalar magnetic potential can be defined only for regions where the current density J is equal to 0. So when you define magnetic potential, you have to write H is equal to minus del Vm for J equal to 0. Okay. Now the SI unit of magnetic scalar potential is ampere, the SI unit. Next we will see the magnetic vector potential. The vector valued function A, whose curl gives B, is called the vector potential. That is, B is equal to del cross A. If there is a sign cross, then that means you are finding the curl of that function, vector function. So if A is a vector function, and if you take the curl of that vector function, you will be getting B. And what is B? B is your magnetic flux density. And here A is known as a magnetic vector potential. Okay. If you are taking any vector function A and if you are finding del cross A, then you will be getting B. And then I can say A is my magnetic vector potential. And A is given by the formula mu0 by 4 pi QV by R Weber per meter. The unit of magnetic vector potential is Weber per meter. where r is the distance from the conductor to the point and v is the velocity of charge. This one, the conductor to the point. The distance is r and v is the velocity of the charge. Next we will see magnetic flux. This is similar to electric flux. Electric flux means electric field lines. Magnetic flux means magnetic field lines. Now magnetic flux through a closed surface psi is equal to surface integral B ds, and this is the Gauss law for magnetic field. Okay. Now we know B is equal to del cross A. Now psi is equal to, in place of B I am substituting del cross A, integral del cross A ds. Next what I am going to do is I am going to apply Stokes theorem. In Stokes theorem it is said that if for any vector you can write the surface integral of del cross a vector. Here A is my vector, so del cross A of ds is equal to line integral of A dl. So instead of this term I can write this one, right? If I am comparing 1 with 2, this term and this term is equal. So finally I can write phi is equal to line integral of A dl, where A is a vector or otherwise known as magnetic vector potential. Okay, this is another expression for magnetic flux in terms of magnetic vector potential. Next we will see the relation between magnetic scalar potential and vector potential. Now this is a relation connecting E and B. E is your electric field intensity and B is your magnetic flux density. Okay, electric field intensity, magnetic flux density. Del cross E is equal to minus dou B by dou T. This relation is very important. And we know B is equal to del cross A. So I am substituting this equation 2 in 1. So I can write del cross E is equal to minus dou by dou T of del cross A. Then what I am going to do is I am taking this del out. So that is equal to minus del into dou A by dou T. Then this is taken to the left hand side. So I can write del cross E plus del into dou A by dou T is equal to 0. Del is taken as a common factor. So del into E plus dou A by dou T is equal to 0. Now we have H is equal to minus del Vm, which is our magnetic scalar potential. At the same time we have this expression also, del cross H is equal to J. Now what I am going to do is I am going to substitute this H in this expression. So I can write del cross minus of del Vm is equal to J. Okay. So in the case of magnetic scalar potential, this definition is valid for J equal to 0, right? We discussed earlier, J should be equal to 0. So I am substituting here J equal to 0. So finally I will get del cross of minus del Vm is equal to 0. Now I am comparing these two equations. So finally I will get E plus dou A by dou T is equal to minus del Vm, where this Vm is our magnetic scalar potential and this A is our magnetic vector potential and E is an electric field intensity. So this is a relation connecting magnetic vector potential and magnetic scalar potential. And that's all in this section, and thank you.